NS2 and P6, but helium is an exception with the outermost configuration NS2. Now, since they have fully filled orbitals, they are very stable and chemically inert under normal conditions, and hence the name inert gases. But under special conditions, the higher Van Wels have been observed to form some compounds. For example, xenon reacts with fluorine to form fluoride. So the name inert gases has been aptly changed to noble gases. The second group proposed by Bohr was normal or representative elements. They belong to the groups first A, second A, that is the alkali metals and alkaline earth metals, third A, fourth A, fifth A, sixth A, and seventh A, that is P block except the noble gases. Their outermost electronic configuration is NS1 to NS2P5. So their outermost shell is incomplete. They consist of metals, non-metals, as well as metalloids. They are found in abundance in nature and are chemically active, hence the name normal or representative elements. The transition elements. The elements belonging to the groups 3rd B, 4th B, 5th B, 6th B, 7th B, 8th, 1st B, and 2nd B, that is D block, constitute the transition elements. Their outermost electronic configuration is N-1, D1 to 10, NS1 or 2 in the ground state or excited state. Their inner shells are filled, but their ultimate and penultimate shells are incomplete. There are 4 series of transition elements, with 9 elements each in the first 3 series, and the elements after helium are being added to the 4th series as they are being discovered. The last group is the inner transition elements group, constituted by the elements of the F block of modern periodic table. They belong to the group 3rd B. They consist of 2 series of elements with 14 elements each. The first inner transition series of elements consists of elements from atomic number 58 to 71 known as lanthanides, and the second inner transition element series consists of elements from atomic number 90 to 103. They are known as actinides. Their outermost electronic configuration is N-2, S2P6D10, F1 to 14, N-1, S2P6, D0 to 1, NS2. The inner shells, that is the shells up to N-3 level, are completely filled. This table gives a broad idea about Bohr's classification. The first group is the inert gases, which consists of helium and zero group elements. The second is the normal elements or representative elements, which consist of S block elements and P block elements except the noble gases. They consist of metals, non-metals, and metalloids. The third group, that is the transition elements, belongs to the D block, and the inner transition elements has F block elements. Now let us solve some simple problems based on the concepts that we have just discussed. The first example, in Jovirinus triads, the 3 elements were grouped horizontally, vertically, diagonally, or horizontally and vertically. Now, if you remember, the triads were like chlorine, bromine, and iodine. They were grouped vertically. That is, the elements belong to a single group. Therefore, the correct choice will be B, that is vertical. Next example, in Lothar-Meyer's curve, which of the following quantity is plotted as the abscissa? Now, if you remember the graph, the vertical axis, that is the ordinate, was the atomic volume, and the horizontal axis, that is the abscissa, was the atomic mass. So the question asks us, which of the following quantity is plotted as the abscissa? This is the atomic mass or the atomic weight. So C is the correct choice. Next question, which of the element occupies the peak position in the Lothar-Meyer curve as an exception along with the alkali metals? If you remember, alkali metals occupied the peak positions since they have the lowest density. Along with that, helium, in spite of being an inert gas and having different properties, also occupied a top position. It was also one of the defects of Slothermer's atomic volume curve? So our answer is choice B, that is helium. Which of the following group of elements occupy the descending part of Slothermer's curve? It was the alkaline earth metals. Since alkali metals occupy the top positions, transition metals occupy the lowest positions. Halogens were on the ascending part of the curve and noble classes were placed just before the alkali metals. So alkaline earth metals is our correct choice, that is B. Next question. In Mendeleev's periodic table, the horizontal columns were known as, the first choice is groups, second periods, third blocks, or the last choice, none of the above. If you remember, Mendeleev called the vertical columns as periods and horizontal columns as groups. Whereas in the modern system, we call the vertical columns as groups and horizontal columns as periods. So for this question, the correct choice, that is the horizontal columns, were known as groups, that is A. Next question. The three elements whose properties were predicted by Mendeleev in his periodic table were, the choices are boron, scandium, gallium. Second choice, boron, aluminium, silicon. Choice C, boron, gallium, and germanium. And choice D, scandium, gallium, and germanium. The correct answer is D, that is scandium, gallium, and germanium, which Mendeleev called eka boron, eka aluminium, and eka silicon, respectively. Last question. How many elements among the representative elements are non-radioactive liquids? Now, the representative elements consist of the S block elements and the P block elements, except the noble gases. Now, S block has two liquids, that is cesium and francium, whereas P block also has two liquids, gallium and bromine. Out of these four, francium is radioactive, so we are left with three non-radioactive liquids. So our answer is B, that is 3. Hello students, today we will begin with the first part of periodic trends, in which we are going to discuss periodicity exhibited by various properties in the elements. In this part we are going to take up atomic radius, atomic volume, ionization energy, and electron affinity. Those properties of the elements that depend upon the location of the element in the periodic table are known as atomic properties. For example, atomic radius, ionic radius, ionization energy, electronegativity, electron affinity, etc. The atomic properties as well as the chemical properties show periodic variations. Before we begin with periodicity properties and the reason of periodicity, let's get some clarity on some basic definitions. The first of them is effective nuclear charge. It can be defined as the net nuclear attraction towards the valence shell electrons. Now we know that the nucleus is surrounded by electrons which revolve around it in various levels. So the attraction of nucleus on the outermost electrons is not as strong as it would have been in the absence of the inner electrons, that is, those electrons that revolve closer to the nucleus. We can represent effective nuclear charge in the form of a simple mathematical formula, which is Z star is equal to Z minus. Here Z star is equal to effective nuclear charge, Z is the nuclear charge, and S is the screening constant. Screening constant brings us to another term, that is screening effect. Screening effect can be defined as the protection of the valence electrons from the nuclear attraction by inner shell electrons due to the repulsion between the inner shell and the outer shell electrons. It can be quantified in terms of screening constant. Its value for those electrons which are present in 1s orbital is 0.30. For electrons present in sp-d orbitals of n-1 level, its value is 0.85. And for the electrons in sp-d-f orbitals of n-2 level, it is 1.0. Let's have a look at this figure. This atom represents lithium atom in which 3 protons are present in the nucleus. There are 3 electrons out of which 2 are in the 1s orbital and the 1 is in the outer 2s orbital. So the attraction of these 3 protons for this electron, that is 2s electron, will not be as strong as it would have been in absence of these 1s electrons, because these 1s electrons cause repulsion to this 2s electron, and thus the effective attraction of the nucleus on this 2s electron decreases. This is the presentation of sodium with 11 protons in the nucleus and 11 electrons moving around the nucleus, out of which 2 are 1s. 2s and 2p amount to 8 electrons and 1 is 3s electron. So the 3s electron experiences lesser nuclear attraction as it would have been in absence of these inner electrons, because these inner electrons repel each other and this 3s electron, and thus decreasing the effect of nucleus on this 3s electron. The same is the case with the potassium, in which the outermost electron, that is the valence electron, is in 4s orbital and experiences much lesser attraction by the nucleus due to the presence of these inner electrons. Periodicity. Periodicity is the repetition of similar properties after regular intervals. While studying the modern periodic law, we learned that the chemical and physical properties of elements are periodic function of their atomic numbers. Now, the electronic configuration of an element is determined by its atomic number. So, the physical and chemical properties of elements are determined by their electronic configuration. We can say that. Now, when electronic configurations of elements are written as a function of their atomic numbers, similar outer electronic configuration gets repeated at regular intervals. Therefore, it is the similarity in the outer electronic configurations which causes periodicity in the properties of the elements. For example, all alkali metals have the outer electronic configuration NS1, hence similar properties are exhibited by them. Now let's discuss the various properties exhibited by the elements and the periodicity in them. So first of all, let's take up atomic radius. Atomic radius is the distance from the center of the